When it comes to graphics cards, many people's first reaction is, isn't this just for gaming? In fact, besides being used to accelerate graphics rendering, a graphics card has another function that you may not know about. Its GPU can be used as an AI chip. In this video, we will focus on the capability of the graphics card to function as an AI chip. First, let's explore the graphics card. When you open it up, you'll see a PCB printed circuit board inside. On this board, the most important component is the GPU chip. Similar to a CPU chip, the GPU chip also integrates tens of billions of transistors. However, the big difference is that the number of cores inside a GPU can reach tens of thousands, while a CPU usually has only a few cores. So why does a GPU need so many cores? This is directly related to the tasks that the GPU handles. I will use an example of a 3D game. Any image you see in the game is processed and rendered by the GPU. Each object in the game is made up of many small triangles linked together. Each triangle has 3 vertices, and each vertex has corresponding coordinates in 3D space. By determining the position of each triangle in space and connecting them, we can create a complete 3D model. Then a corresponding texture is applied to each triangle, allowing the 3D model to be displayed. Although this process seems simple, in reality, the computer has to handle a lot of complex tasks. In the real world, when humans move, the images their eyes perceive also change continuously. To simulate this phenomenon in computer graphics, cameras are used in place of human eyes. When a camera sees an object, it tries to display that object as a 2D image on the screen. First, the object exists in model space, where it maintains its shape through its spatial coordinates. To see what that object would look like in the real world, we have to convert from model space to world space. Since objects in the world are constantly changing from the observer's perspective, their coordinates in the world must change accordingly with the movement of the camera. World space gradually gets converted into camera space, which is then turned into a view that can be displayed on the screen. The question is, how are these different spaces converted? Let's take the coordinates of a model vertex as an example. When this coordinate is moved into world space, its information changes. We can determine the model's position as it changes in terms of location, scale, and rotation before moving it into camera space. Similarly, we can take the camera's coordinates and adjust the rotation values. Then by placing these coordinates, scale, and rotation values into a transformation matrix, calculations are performed. Although matrix transformations may seem complex, they essentially involve basic addition and multiplication, something elementary school students can grasp. The final result is the x, y, and z values that correspond to the 2D. That is the calculation process for just one vertex. However, in games, the scenery is usually quite complex, with hundreds of thousands or even millions of vertices needing to be computed simultaneously. These simple yet massive calculations don't necessarily have to use the CPU's resources. To free the CPU from these computational tasks, GPUs were created, designed specifically to handle simple parallel computations. A GPU has thousands of cores, and when you give it a large amount of calculations, it immediately distributes the tasks to the logic units across these cores for processing. Thanks to this, the calculations are completed and returned quickly. That's why, when playing games, you don't feel any lag. So how can a GPU achieve such large-scale parallel computing? Below are 100 computational tasks requiring the use of a GPU, with each task represented by a thread. The ideal situation is to assign these 100 threads to 100 GPU cores for independent processing. However, the problem arises when the GPU has to handle a huge workload. If there are 1 million tasks to process, we would need 1 million GPU cores, which is obviously not feasible. But if we distribute these 1 million tasks across 1,000 GPU cores, the process of dividing and managing these tasks becomes very complicated. To simplify, we can use 1,000 GPU cores and divide them into 10 groups, each containing 100 cores. This makes task assignment much easier. Similarly, for 1 million tasks, we can divide them into groups of 1,000 tasks and then split them into 1,000 different groups. However, the problem is that each group has 1,000 tasks, while the corresponding number of processing cores is only 100. To further optimize, we can batch the 1,000 tasks that are ready for each group. Continuing to group, 100 processing cores are divided into 10 smaller groups. As a result, 100 tasks can be allocated and processed according to these 100 cores. GPUs are designed to handle tasks with extreme efficiency, catering to high-performance computing. However, GPUs were initially only meant for graphics rendering, so how did they become AI chips? This is largely tied to the development of AI, where AI models require performing large-scale parallel calculations, especially matrix operations. To conduct deep learning and train models quickly, GPUs are an ideal choice as they meet the computational demands of large AI models. However, many other manufacturers also provide dedicated AI products. So why has the chip become the center of AI? Is NVIDIA the top choice in the AI field? This brings us to CUDA, a key technology in NVIDIA GPUs, which has been a crucial factor in their rise to prominence. In 2007, to build a general parallel computing architecture, NVIDIA launched the CUDA Parallel Computing Platform and Programming Model. Since then, every generation of GPUs has supported CUDA, allowing anyone to develop on this platform. Developers can purchase GPUs based on their strong computational needs to meet the processing demands of their projects. For example, when you write a piece of CUDA code, when that code is sent to the GPU for execution, the GPU will retrieve data from memory, and the CPU will notify the GPU to run the program in parallel. The GPU automatically divides the task into 100 threads and then assigns them to 100 cores for calculation. The programmer doesn't need to worry about how the threads are specifically distributed. When CUDA was first introduced, it wasn't very popular because graphics cards were mainly used to accelerate graphical rendering, and the commercial value of CUDA wasn't apparent. This made it difficult for many companies to develop platforms similar to CUDA. However, when AI began to boom, developers could use CUDA to tap into the vast computational power of GPUs, making the CUDA platform very attractive to developers due to its strong performance. ChatGPT is a prime example. They use tens of thousands of NVIDIA GPUs to train their AI models. This has helped ChatGPT become one of the most well-known AI models in the world. CUDA has also become NVIDIA's greatest and hardest to overcome competitive advantage. Most of the world's leading tech companies rely on NVIDIA GPUs through CUDA, with a market share of nearly 90%. This has allowed NVIDIA to build a powerful and nearly unbreakable ecosystem. Furthermore, NVIDIA continues to release AI superchips that push beyond Moore's Law, which is expected to solidify their leadership position in the future and expand even further. The question is, how can NVIDIA dominance be surpassed? And what is the path for other GPU manufacturers?